Okay, we're ready now to take a look at the component form of the dot product. We've introduced what the dot product is, or also known as the Euclidean inner product. It is a scalar product, right, that takes two vectors and outputs a scalar. Now, in order to extend this dot product or this Euclidean inner product to vectors in n space, we're going to look at this component form. And most of you are familiar with this. Sometimes this is the way it's first presented. I'm going to prove it using the law of cosines. Now that's back in your trigonometry days. Just a refresher, for any triangle with angles capital A, B, and C and opposing opposite side lengths little a, b, and c, we have these three relationships, and they're all basically the same. That this side a squared is equal to the sum of the squares of the other two sides minus the product of 2 times the product of the two sides that are opposite a, and the cosine of the angle between them. So again, that's true for any side length. So like b squared is equal to the sum of the squares of the other two sides minus 2 times the product of those two sides and the cosine of the angle between them. And so this is the law of cosines. I'll just have you note that this works for any triangle. In particular, if, say, angle A were a right angle, if we had a right triangle where this was the right angle and then little a would be the hypotenuse, notice that cosine of 90 degrees is equal to 0. This term goes away, and what do you have? You have the Pythagorean theorem. Yeah, so the law of cosines is, in a sense, is sort of an extension, if you will, of the Pythagorean theorem to arbitrary triangles, oblique triangles. So to prove this now, I'm going to prove it in 2 space, the component form, and then we will extend that idea to n space. So I'm going to deal with two vectors u and v, arbitrary vectors in 2 space. So just these are the components here. Just to remind you, here is the norm of vector v. All right, square root of the sum of the squares of its components. Same thing for the norm of vector u. And further, if I square both of these, I just want you to note that we get these relationships, that the square of the norm of any vector is essentially equal to the sum of the squares of its components. And then I just want to take a look at the vector v minus u. We'll see where that comes into play, and here's its corresponding components. So what I want to do is take a look at a picture of this, see how law of cosines comes into play. So let's suppose I have a vector v here, and let's do a different color for vector u. Let's just put it this way. I'm going to put them both in the first quadrant. I mean, I can put them anywhere I want, but this will help with what we are trying to see here. So the angle between these two vectors, right, is theta, and I'm going to now draw a vector from the terminal point of u to the terminal point of v. I'm going to draw it going in this direction. And remember, we talked about this. This vector is the vector v minus u. So you might want to see how that is. We've talked about that previously, but going from the terminal point of u to the terminal point of v, that's going to be the vector v minus u. And so we have this triangle. Do you see the triangle? And so we're going to use the law of cosines to do the following. The side opposite the angle theta is the norm, or the length, right, of v minus u. So the norm or length of v minus u, so that's the side opposite the angle theta. So by the law of cosines, what do we say? The square of that side length is equal to the sum of the squares of the other two side lengths. So what's the other two side lengths? Well, what's the length of vector u here? That's the magnitude of u. So we square that, and we add the square of the length of this side, which would be the magnitude of v squared. And then we have what? Minus 2 times, right? Remember, minus 2 times the product of the two other sides and the cosine of the angle between them. So this would be length of this side is the magnitude of u, magnitude of v, times the cosine, which we've called that angle between them, theta. And so here is the law of cosines applied to the situation. So you might be wondering, what does this have to do with the dot product? So let's look at that definition of the dot product. I should have started with that, but let's take a look at that definition again. Here it is, right? The dot product, or Euclidean inner product of two vectors u and v, norm of u times norm of v times the cosine of the angle between them. Looking at that, notice right here at the end of this equation that we have from law of cosines, do you see it? There, right there is the dot product. Okay, and here's the thing. These other things here I can write in component form. In fact, we kind of talked about it up here. And so I can express this dot product in terms of the components of u and v. And I just need to do a little algebra to solve this. So what I'm going to do is I'm going to, this is minus 2 u dot v, right? I'm going to add 2 u dot v. Remember, u dot v is a scalar. So I'm going to add 2 u dot v to both sides of the equations. And I'm going to subtract this to get it over there. So I'm going to have 2 times u dot v, and I'm going to be solving for u dot v here in a minute, is the magnitude of u squared plus the magnitude of v squared minus, all right. And then to solve for this, I'm just going to multiply both sides by a half. And so let me do 1/2 times all this stuff. Now I'm going to rewrite this stuff in terms of its component form. So first of all, what's the magnitude of u squared? Well, we already talked about that. That's u, the sum of the squares of its components, u1 squared plus u2 squared. And what's the magnitude of v squared? Well, that's going to be v1 squared plus v2 squared. And then I'll put in parentheses here, what's this thing going to be? Well, it's going to be the norm of this vector squared, again, just like over here, will be the sum of the squares of its components. What's the components of v minus u? The components of v minus u are these. So it's this squared plus this squared. Now, a little algebra here. Let's square this. So remember how to do that. I hope you do. Make sure you realize that is not v1 squared minus u1 squared. That is v1 squared minus 2 u1 v1 plus u1 squared. Whoops, u1 squared. Okay, and then this, similarly, is v2 squared minus 2 u2 v2 plus u2 squared. And now we just need to do a little simplification here. So I get u dot v is 1/2. And what is all this stuff here? So this is a bunch. What does it all simplify down to? Well, check this out. u1 squared, now look at this, minus what? u1 squared. Distribute this minus sign through, minus u1 squared. So the u1 squares, those are kind of gone. Kind of check those off our list. And then u2 squared minus u2 squared. Those are going to go away. v1 squared minus v1 squared, that's going to go away. And v2 squared minus v2 squared. Look at that. Everything goes away. And what are we left with? Well, minus, that's 2u1 v1. And then minus plus 2u2 v2. So hopefully you followed that simplification. And now all that's left is to distribute this 1/2. And what do we get? The dot product u dot v is equal to u1 v1 plus u2 v2. Okay. Now this is really going back to when we started talking about matrix multiplication. I called that a row multiplied by a column. I said that was the dot product of a row and a column. And some of you remember me saying that, I hope, and knew what I was talking about, but this is where it comes from. So we can now extend this idea to n space. We can extend this idea to n space. And so here's the definition of the Euclidean inner product. If u and v are vectors in n space, then their dot product is defined this way. You see how we extended that idea. So some properties of the dot product. Here's an important one. For any vector in n space, the dot product of the vector with itself, if you think about that, what's going to happen? It will be v1 times v1, which is v1 squared, v2, v2, v2 squared, and so on. But the sum of the squares, that's just the norm squared. So it's real important that the Euclidean inner product is defined by the norm here, the norm of the vector squared. So that's a real important relationship. In fact, we can go the other way. If I want to do the norm in terms of the dot product, what do? Take the square root. And so the norm is equal to the square root of the dot product, or this to the 1/2 power, right, is the square root. So there's very important relationships that we will use from time to time. Now, 4 important algebraic properties of the dot product. For any 3 vectors in n space and k any scalar, we have this property, which is sort of a commutative property for the dot product. That's pretty easy to prove. The sort of a distributive property of the dot product over vector addition. So u dotted with v plus w is u dot v plus u dot w. Any scalar multiple of a dot product is the same as the scalar multiple of u dotted with v, or u dotted with the scalar multiple kv as well. And then we have this sort of positivity property here, that the dot product of a vector with itself is always non-negative. I mean, you could think about it going back up to here, because it's equal to the norm, which is always positive, squared, of course. So it's always positive, or equal to 0 what? It's only equal to 0 what? If and only if the vector v is the 0 vector. Okay. Now these 4 important axioms we will come back to, because at the end of the course we will be talking about inner products. This is the Euclidean inner product, as it's been called. But we'll talk about inner products more generally and see that the definition of the inner product then can affect the norm and our sense of measure, distance between vectors, and so on and so forth. And inner products have to follow 4 algebraic properties, basically, and these are the 4 properties they have to satisfy. And we'll talk about those later. Some obvious additional properties of the dot product. If I dot any vector with the 0 vector, I'm going to get 0 for that dot product. Now, just a couple things to wrap up with the dot product. If you remember, we solved for theta given the dot product, or we could solve for theta by taking the inverse cosine of this expression. So let's just remind ourselves of how we got there. If this is the dot product, again, going back to this definition, this is not the component form definition, but this is where we started. If I divide both sides of this by the norm of u and norm of v, right, assuming they're both non-zero here, then we get the cosine of theta is equal to this expression. So what I'm saying is I can solve for theta by taking the inverse cosine of this. Now, that makes sense for 2 and 3 space. We can draw all these pictures and these angles. Well, what about 4 space and higher? How do I draw an angle in that situation? You can't, do the geometry there, but we can do it algebraically. But that is provided what? Provided this expression here is in the domain of the inverse cosine function. So you might need to remember and refresh your mind about that. What's the domain of the inverse cosine function? It's the same as the range of the cosine function, which is everything between -1 and 1 inclusive. So as long as this is true, then we can always, at least algebraically, find an angle and descend and extend that notation to vectors in n space. Well, this relationship here actually is true. It's guaranteed by the so-called Cauchy-Schwarz inequality. This is important inequality. It appears in lots of other areas of mathematics, and sometimes it's called just the Cauchy inequality, sometimes the Schwarz inequality, and sometimes some other names. But it's an important inequality to do different areas of mathematics. This one is in this form. Here is the Cauchy-Schwarz inequality for 2 vectors in n space. The absolute value of their dot product. Remember, a dot product can be any real number. A dot product can be any real number. So the absolute value of that dot product is less than or equal to the product of the norms. Of course, the product of norms would always be a non-negative value. But so this is the Cauchy-Schwarz inequality. I'm not going to prove this Cauchy-Schwarz inequality, but I'm going to use it to basically prove this, and that is looking at this expression here. Looking at this inequality here, notice we can divide both sides by this product, right? Positive product, right? Again, assuming u and v are non-zero, then dividing that by both sides, we get this expression here. Since I'm dividing by a positive number, right, both sides by a positive number, that doesn't change the sign of the inequality. Okay, and then because of this, essentially the denominator is always a positive number, so I can rewrite this expression as just the absolute value of the whole thing. It's not going to change anything. The top u dot v, that could be negative, so I still need the absolute value bars around it, but by extending these absolute value bars down below, the denominator is always positive. It's not going to change anything at all. So now we get this expression, which is our expression we've been looking at here. If the absolute value of this is less than or equal to 1, what does that mean? If your absolute value is less than or equal to 1, that means you're within 1 unit of 0. This expression is within 1 unit of 0, what? Between -1 and 1. Okay, and so there it is. This proves this theorem. So we can extend the idea of angle to n space, and that's not really a big thing. I mean, you could do the computation. In other words, given 2 vectors u and v in n space, you can do the computation and you can get that angle. Now there is one certain extension that we are interested in, as that is when this angle is 90 degrees, right, or pi over 2 radians. We know in 2 and 3 space, in that case, the vectors are going to be perpendicular to one another, or what we call orthogonal, and we're going to be looking at that a little bit more in depth in the next set of lecture videos. Okay, so one last thing is just to remind ourselves that we've already talked about this, but dot products in matrix multiplication, right? So again, this is coming back to matrix multiplication, just restating the same thing that we know, that if A is m by r and B is r by n, notice the number of columns of matrix A equal the number of rows of matrix B, and so the product AB is defined, and the ijth entry of that product is this, right, which is essentially what? A dot product of the ith row of A and the jth column of B. That's exactly what that is. And so if the row vectors of A, row 1, row 2 going down, right, column vectors of B, C1, C2 going left to right, then the matrix AB can be expressed as just these dot products, right? First row times first column for first row, first column entry. First row, second column for the first row, second column entry, and so on, right? So it's just exactly the way we defined matrix multiplication. Okay, so we will go on to talk now a little bit more about orthogonality in the next set of lecture videos.